All right, so I processed all your feedback that you gave me last time, and it seems like a lot of you guys, some of you are reasonably comfortable with science. Many of you are very uncomfortable with science, haven't had any science since like your sophomore year of high school or something like that, and even that was kind of marginal. So I am going to, based on the belief that education only matters if it is an emotionally impactful and supportive experience, I'm not going to traumatize you and just dive into some hardcore biochemistry. In fact, we probably won't have any hardcore biochemistry this semester, but we are going to do it. It's the name of the class, right? So without presuming any of your science background, I'm going to give you all the very basics of general chemistry and chemistry. Today is chemistry. I'm just giving you some chemistry so that we're all on the same page, all right? I apologize for those of you to whom this material is going to seem tedious and simplistic and boring, but I am really not taking anything for granted, okay? So, climbing the ladder of life. You really can think of life along a size scale, right? So we live in this realm here. What the me that is speaking to you is on the organismal realm. I'm an organism, right? I'm a human. And I'm communicating to you on that level. But I am made up of organs, organ systems that are made up of tissue, that's made up of biomolecules, that are made up of smaller molecules, that are made up of atoms, right? And as an organism, you can look higher into ecosystem level and biosphere levels of life. Come on in, buddy. What's your name? DeVito. Just because now you are immortalized in the recording as being like... Oh, David. Okay. So I'm going to take you up this ladder a little bit and help you see the parts. So just a little bit of history. I try to incorporate a fair amount of history into this because I think it's an interesting way to think about science. And it's good. Hey, Will, come on in. No problem. It all goes back to Aristotle, who in this class has not had a class where somebody talked about Aristotle. Probably. Oh, you've never had anyone talk about Aristotle. I'm glad to be your first. Yeah, he works his way into much of Western thought, right? For literally thousands of years, much of Western understanding was based upon Aristotelian thought. So when was this guy? He was in about the 4th century BC. So he had a very complex body of knowledge that we're only going to take some parts of. One of them was a simple concept that complex structures are built from simpler parts. All right, that you can take a complex structure and you can find elements of it that are easier to digest, easier to understand in their isolation, but when combined, they form, complexity emerges. So basically the idea that the emergence of complexity is related to this. It's the other side of this concept. So he also believed, I think we could debate this, but from a philosophical standpoint, from a strict scientific standpoint, I think time has shown this point to be incorrect, but he believed that matter was infinitely divisible. Infinitely divisible. So you can take a cookie and tear it in half, break it in half, and give it to a buddy. And then he can take that and break it in half and give it to his friend, and she can break that, and so on and so forth, forever and ever and ever and ever.
Good deal.
Yeah, you get a much bigger chunk of the cookie than the last person. There is no last person. So, and he has other ideas that we're going to come back to related to what he thought the four elements were, et cetera, as we talk about, we move forward. But this idea that matter is infinitely divisible, there was a guy named Democritus that lived about the same time, and he kind of lost the minds of the time. His philosophy was that there were atmos, that matter did have a fundamental unit. There was a fundamentally irreducible unit to matter. And people, they just didn't buy it. They didn't buy it. He really gave us the first atomic theory, the idea that matter was indivisible. And it took about 2,000 years for really the first person to sort of revive this concept was Leibniz, the mathematician, who came up with the concept of a monad, but that's some esoterica. All right, so the bottom of the ladder that we're going to start with is just atoms. And I'm going to talk today about what atoms are, how they're structured, and how they combine to form molecules. And eventually, next time, or the next several weeks, we're going to talk about macromolecules, right? So you can take smaller molecules and make macromolecules, or the biomolecules that make up living systems, right? And biochemistry, when I talk about biochemistry, it's really in this realm of macromolecule that we're going to spend a lot of time thinking about. What are the macromolecules? Fats, proteins, carbohydrates, and what do they do? How do we use them? And how do they combine to form the other steps up this chain, right? Because we're interested in the organism. You're interested. You didn't come into this class thinking, oh, I wonder how eating a diet rich in N-acetylglucosamine is going to affect my hyaline cartilage. Maybe you're not, because that's tissue level. You're thinking, how is it going to help me, the organism? How am I going to be healthier? Or what is it doing to me? My food choices, what is that doing to me? So to be able to connect this level of macromolecule to where you guys are mostly interested, which is the organism, we will have to talk at various points about these other rungs in the ladder. Okay, we'll have to talk about organ systems and organs, how various organs work in the body. What is the effect on certain tissues? I'm not going to make it all about that because this is a 100 level class for non-majors, and that's really, you're talking about a whole major to be able to fully cover all the concepts that are involved in this. But I'm going to give you a little survey. I love Aristotle. Yes, talk about it. Okay. So how do we even know all this stuff exists? There are different ways that we can probe these levels of size scale. We can probe them by sight, right? That's one way. We can actually just see them, tangibly see them. And so this diagram, I like this diagram because it sort of gives you a sense of scale and how humans are able to probe that scale. So if you look at this, the unaided human eye, the smallest thing that an unaided human eye can see, poetically, truly beautifully to me, is the largest of human cells. It is the human oocyte. So a human egg that would emerge from a female's ovary is the smallest size scale that can be seen with the human eye. That's sort of beautiful. There's a beautiful poetry to that. my mind. And then there is the realm of the compound light microscope. Last year, I didn't use light microscopes at all in the lab, but because I'm completely revamping the lab, I've decided to add the microscope because it's kind of fun to look at things really close. I really like looking at things up close, and I think it can be kind of instructive in a lot of ways. So we're going to use some compound light microscopes at various points throughout the semester. We'll do some scrapings of the inside of our mouths and see what's in there, and we'll look at different types of wheat under a microscope and look at the germ and the endosperm layers of wheat, etc., etc. But we can see down past the level of a cell, we can identify organelles in a cell, like mitochondria. And we can see little bacteria with a compound light microscope. And then to get really small, there are various forms of electron microscopy, which is where you're shooting a beam of electrons at something and recording the results of that interaction and forming an image from it. So I'll show some electron micrographs at different points, and it's really just a method, another method. It's not based on light that we see where you're looking through a lens. It's based on a beam of electrons that you're shooting at a surface, and they're bouncing off and being collected by a detector. And it's, yes, sir, David.
What are you looking
Any part of the cell, you can look at collections of cells, or you can make out proteins that are embedded in the surface of a cell, for example, or you can make out, like fine details of mitochondria, for example, or electron microscopy is a very powerful tool for visualizing some stuff. I'll show you some pictures. You'll see it. It's pretty cool how it works, the kind of images that we get to see. All right. So here's our high school chemistry review, atoms. So there are really three parts to three particles, I should say, subatomic particles that make up an atom. They're called the proton, the neutron, and the electron. Who remembers anything about any of those terms? Do those terms ring anybody's bell? Okay. So tell me some stuff about them. We'll start with the charge of a proton. Is there a charge on a proton?
Yes.
Okay.
Proton is positive.
Are you positive?
Yes.
Okay. All right. And what about a neutron? Okay. See it.
Nothing. It's not negative charge, but it's not positive.
So there is no charge on a neutron, is what you're saying. Does everybody agree with him? Does anybody disagree with that? He's right. Yeah, he's right. He's right. So all of this actually reminds me of a joke. There's these two hydrogen atoms. They're in the hydrogen-helium atom wars, and they're shooting, and one of the hydrogen atoms goes, "Ah, I'm hit! I've lost an electron." And the other proton says, "Are you sure?" And he goes, "Yeah, I'm positive." An electron. So electrons are negative. I know that's a bad joke, but protons positive, neutrons neutral, no charge, electrons negatively charged. And what does negative and positive mean? These are arbitrary designations, right? They're just opposite and equal in charge. All right. Now it's a little bit trickier. What about mass? What is the mass of a proton? What do you think? Well, remind me of your name, please. Yeah, you. Josh. Hey, Josh. What is mass? It's kind of hard sometimes to come up with a definition of mass, isn't it? Anyone want to help him? I put him on the spot. Yeah. You get the cookie. Thank you. invisible cookie. That's right, yeah. So mass is just, explicitly, it's the way, it's the amount of something, but it's also the way, mass is the way that matter deforms space, is like the most sort of physical scientific description of it. But we experience mass on Earth as weight, right? So, for example, you would weigh, or I would weigh, 145 pounds here on Earth, but my mass in kilograms is, I don't know, what is that, like 60 kilograms, something like that? And if I went to the moon, my weight would be, I don't know, 100 pounds, but my mass would still be 60 kilograms. There's the same amount of me, right? There's the same amount of me. So people often equate grams and pounds. They're not actually the same. We experience them as the same because it's all here on Earth, right? But the idea of pound is actually a force. Pound is a force. It's not a mass. And a kilogram is actually a mass. It's a measure of how much of something. So do we measure protons in kilograms or grams? Well, protons are pretty small. Pretty small. What are we going to do? How are we going to do it? Yeah, AMUs. The answer's on the board. Good. I often ask questions that where the answer's on the board. That's right. We're going to make something up. It's called an atomic mass unit. They made it up. They made the unit up. An atomic mass unit is 1/12 the mass of one atom of carbon-12. All right, and we'll get to what carbon-12 even is. So the mass in AMU of a proton is about 1. It depends where that proton is, okay? And the mass of a neutron is also 1. Electrons, in contrast, are extremely light. It's only 1/1800th of the mass of a proton or a neutron. All right, so those are the parts of an atom. And we need to know about charge because we're going to talk about some charge interactions. For example, salt. We're going to need to talk about salt. What is a salt? How does a salt work? What is it? Why do we like it? It does taste good. Why? All right, so remember, food is made up of atoms. Here's the periodic table of the elements. All right, and you've all probably seen this before. Here are 3 elements. I just picked 3 out. Fluorine, cobalt, and iodine. These are ones that you may find in food. Okay, and we need them to greater or lesser degrees. Okay, where are they? How do we find them on the periodic table? Does anybody want to?
I mean, the periodic table is semi-organized. It's not completely organized by atomic hydrogen. I guess you could. Atomic.
Okay.
Is the number.
Help him. Yep, he's right. He said some right things. I don't agree with everything he said. Help him out. Yeah. That's it. There it is.
Oh, you wanted me to find it?
Yeah, well, I just wanted to hear what you're going to say. Sure. Yeah, F is fluorine. It's it's number 9 in the periodic table. And the part that I took exception to is the idea that the periodic table is semi-organized. Periodic table is exquisitely organized. And
It's as best as it can be. It's not perfect.
I would say it's quite perfect. Yeah, and I'm gonna help you see that perfection here because if you understand how the periodic table is put together a little bit, it tells you so much information. The crazy way it looks like it's haphazard. Why didn't they just put it in a big square?
It didn't work.
Well, it didn't actually work. It didn't actually work. This is a better organization, and we're going to see why in a bit. So fluorine is number 9 there, and cobalt is number 27, And iodine, where is it? It's way down there. It's number 53. So Graham had pointed out that there are these things called atomic numbers. And if you look, starting with hydrogen and then going to helium in the other column in that first row, and then going to the second row, lithium, and then beryllium and boron and carbon, they have little numbers in the upper left-hand corner. That number is the atomic number. All right? And it is useful to know that the atomic number is how many protons. It is how many protons. So, Alex, how many protons are in fluorine? 9. Yeah, great. And cobalt. What about cobalt? We said it earlier. It's in the mid. 27. You got it. And then iodine is 53. All right. You don't need to know those numbers. Don't memorize that. I'm not asking you to memorize the periodic table. I just want you to be able to understand it a little bit. Yeah, okay. So that is the number of protons in an atom. An atom is an element, or an atom is that element because it has that number of protons. Fluorine, if an atom has 9 protons, it's fluorine. If it doesn't have 9 protons, it's not fluorine. Always and forever. All right? If an atom has 27 protons, it is cobalt. If it doesn't, it is not cobalt. Now, the number of neutrons is a little bit tricky. And the reason I'm even talking about this is because we're going to do some experiments where we're going to take your hair off your head. I'm going to get a little piece of your hair somehow. Maybe you just comb, it'll come out. And we're going to send it in for elemental analysis. We're going to look at the elemental analysis of your hair, and we can see how much meat you eat, or whether you're from Europe or North America, based upon your hair. And that's based truly upon the understanding of what a neutron is. Oh, man. So the thing about neutrons is the number of neutrons within an element. Say we have a whole collection of fluorine, for example. The number of neutrons can vary atom to atom amongst the fluorines. All right? Can and does vary. So if I were to ask you, looking just at that table to fill out the number of neutrons, you wouldn't be able to. You couldn't guess. You really wouldn't be able to guess. You could come up with a kind of a hypothesis, but you wouldn't be able to give me really the exact answer. So I'm just going to put some numbers in there. These are some values of the neutrons. Actually, it's the number of neutrons in the most stable form of those atoms. So we know that some atoms are radioactive, right? It's like uranium or whatever. Yeah, they decay. And so there are atoms of elements that have different numbers of neutrons. Some of those arrangements are more stable than others. If they're not stable, they fall apart, and they give off energy when they fall apart. That's called radiation. Every atom has a most stable form, and that's the number of neutrons that I put up there. All right? You wouldn't be able to know that just off the top of your head. Yeah, David.
When they're talking about like.
Sure, yeah. Mm-hmm. Yeah, so hydrogen, atomic number 1, had, and I'm not talking about hydrogen gas, which is actually a diatomic molecule, hydrogen bonded to itself. I'm talking about hydrogen, a single atom, its nucleus is just a proton, all right, in most hydrogen, like 99.9%. But there's like, 1% or something like that of the hydrogen out there that actually has a neutron in the nucleus as well. And we call that deuterium. Right? Deuterium is not radioactive. But if you have water that is made up of deuterium molecules with the oxygen, that's called heavy water. And they call it D2O instead of H2O. D2O is not dangerous unless you had a whole container of it and you started drinking it. It can actually mess up through like something that is way beyond my ability to explain to you without a lot more background, but it through something called the kinetic isotope effect, it incorporates D2O, deuterium, into your body, and it throws off the equilibrium, the dynamics of chemical reactions in your body. So yeah, you shouldn't drink a whole bunch of D2O, but it's not like poisonous, like it's going to make you barf or something like that. It's just going to kind of, screw you up. Tritium. So there is another form of hydrogen called tritium that has 2 neutrons and 1 proton. That is super unstable and is very radioactive. You definitely do not want to be around that stuff. All right. They use that as like a radio label sometimes in science, but you like special training and all that stuff. That's very rare. Deuterium or D2O, they get it. They can get it. They can make it, but they can also get it like from the Mariana Trench. So like the bottom of the Mariana Trench is like heavily enriched in deuterium, D2O. It's heavy. It's heavy water. It goes to the bottom.
Wait, heavy water isn't like water that is radioactive?
No. That would be with tritium. There would be some of that down there. I guess the water in the bottom of the Mariana Trench would be a little more radioactive. Yeah, kind of interesting. I would go down there if I could. Yeah. All right. So the idea of mass number. This is the important one that we need to get to so that we can talk about what's called isotopes. And isotopes are going to be what we're actually measuring when we take a chunk of your hair or when we talk about corn and nitrogen and all these different things. All right. So, but an isotope requires an understanding of what the mass number is. It's pretty simple, not high-level math here. A mass number is just protons plus neutrons. So, what's the mass number of this fluorine that I put up there? 19. Okay. Am I trivializing this? No, I hope not. So, cobalt with 32 neutrons is going to be what? 59, okay? And then iodine, this most stable isotope of iodine has 74 neutrons. So that's 127. All right, really simple. So that's the mass number. That's the mass number. It's not actually the mass as measured in AMU. All right, and I'll explain that in a moment. The actual mass of fluorine 19 or cobalt 59 or iodine 127, which is what we would call those versions of those atoms, has these real fractional values that are measured in AMU. And the value is close to the mass number. It's close to the mass number, but it's not exact. And this is because the definition of an AMU that I gave you was 1/12 of the mass of carbon-12. So let's look at carbon. Where's carbon on the carbon symbol is C. Where's carbon on there? Number 6. Yeah, and so carbon-12, how many neutrons would that have? Well, no, 12 minus 6 is 6, right? So it would have 6 neutrons and it has 6 protons because it's carbon. An AMU, by definition, is exactly 1/12 of the mass of carbon-12. But as you stick more neutrons and protons into a nucleus, some of that mass gets turned into energy as it holds that nucleus together. All right. So we know that E equals mc squared, right? That the famous Einstein thing. You didn't think you'd take a class that had E equals mc squared in it. Well, here it is. Energy equals mass. Energy equals mass times a constant, which happens to be the speed of light, which is a fundamental property of the universe. So energy is mass, and some of that mass gets converted into energy when you add them together, which is why the exact mass doesn't equal the mass number. Okay? Is that all? Is this any of this review for anybody, or is this new stuff? A little bit? New mostly? Okay. Well, I said that atoms of a particular element can have different types, different numbers of neutrons. We call those isotopes. We call them isotopes. So an isotope of the same element has the same number of protons because they're all that element, right? All carbon has 6 protons, but different numbers of neutrons and consequently different mass numbers. So we'll look at chlorine. There are 2 stable isotopes of chlorine, chlorine 35 and chlorine 37. So looking at that, who can tell me what the number of protons is? So chlorine's atomic number is 17. What do you guys think? You need a chance to talk to your neighbor. Talk it with your neighbor for a minute. You got neighbors. Meet them. You got it? What do you think? Okay. And what do you think?
17.
Okay. And what do you guys think over on that side of the room? 17, your group? Okay. Well, let's hear from the 17s. Defend it. Why do you think 17? Mm-hmm. Okay. And you guys said 18. Why do you think 18? Do you have, I mean...
Oh, number of protons. See.
Okay. Okay. That was a good thought. That's a good thought. That kind of thinking is going to be useful, but you hold on to that strategy, and it'll come in handy in a moment. Yeah, atomic number of protons, super easy. Super easy. It's just the number that it is in the periodic table. It's just the number that it is in the periodic table. It's the atomic number. It's the number of protons. Those are all the same. Yeah, okay. So let's assume that this chlorine atom is electrically neutral, no charge. So how many electrons is that going to be? 17. I heard a whisper. Right. Okay. Now let's start using your thinking a little bit. Let's start using this thinking that you have, this subtractive thinking. Talk to your partners again and figure out the number of neutrons and the mass number. Okay. Who's confused? You got it? You good? No? A little bit lost.
We got this. Y'all are gonna get.
Okay. Okay, should we let these guys redeem themselves?
Yeah.
Okay.
Super ready, the redemption tour.
Let's hear it. Okay. All right. Who disagrees with that? Because they could be wrong. They've already been wrong, right? Probably won't be the last time. They're right. Does anybody not see where they got that? Don't be shy. Yeah.
Where do you see that?
Yeah. So if you see right there at the isotope, maybe I didn't walk you through this little diagram I had on the lower right-hand side. So here's chlorine 35. You'll see that whole thing is the nuclear symbol. The Cl is the elemental symbol, but then that number that's a superscript preceding it, that is the mass number. That is the mass number. So when you see, we'll talk about carbon 12 and carbon 13 And when we talk about those, you're going to see a little superscript 12 and then a C. Or you'll see a superscript 13 and a C. All right. So when they were looking at that, they must have absorbed that little thing, the nuclear symbol diagram, and then saw, okay, well, chlorine 35 must be the mass number, or 37, depending on the row. And then they just did simple subtraction. They subtracted the number of protons from the mass number and figured out what the number of neutrons was. Does that make sense? Everybody with me? Yeah, cool. All right. So, as I said, the exact mass is some fractional number that's near the mass number. All right. When you're looking at these words, when you have the word number in there, it's not going to be some fractional number or something like that. It's going to be an actual whole integer. All right. So the mass number is an integer, whereas the exact mass is going to be some fractional number measured in AMU. All right? And it turns out that we don't have, it's not equal. We don't have equal amounts of chlorine 35 and chlorine 37 in the world. We have chlorine 35 is more stable, and consequently about 75%, 75.8% of the chlorine atoms, when you shake out some salt, some sodium chloride onto your French fries, 76% of it is chlorine 35 and 24% of it is chlorine 37. All right. I decided to not go here, but you can get what's called an average atomic mass by multiplying the exact mass by its percent natural abundance for each of the stable isotopes, then adding it up. And that's a very useful number that we may or may not actually need. If we do need it, I'll teach it to you more explicitly later. But percent natural abundance is a useful concept. All right, so simple summary. Food is made up of atoms that have different isotopes. Remember that. Okay, so now, how does the periodic table of elements reflect the electronic structure of an atom? Knowing what we know, so I want to start going from atoms to bonding them together to make molecules. All right? I want to make molecules, but I'm going to tell you this, that bonding is all about electrons. We're not doing anything nuclear in here. Like tearing nuclei apart, that's some like fusion, fission, nuclear reactor, atomic bomb stuff. This is food, right? So we're not going to tear nuclei apart. We're like chemical reactions is just rearranging the electrons around these big nuclei that never change. Does it make some sense? So it's all about the electrons, okay? And knowing what you know about the periodic table, which is only a little bit, I've only given you a little bit so far, but you already know more than you think. Knowing what you know about atomic number and the structure of the periodic table, how does the periodic table reflect the electronic structure of an atom? Okay, also assuming that all electrons are neutral. What do you think, Theo? You kind of waved at me.
Like the amount of electrons.
Whoa, yeah, you're like 2 slides ahead of me. Good job.
So it's like
Now you lost me. No, certain isotopes have more neutrons, but neutrons don't actually have any effect on the electrons. They don't. Because remember, neutrons are neutral. And so protons are positively charged and electrons are negatively charged. And those are the things that are interacting. So if an atom is going to have an overall net 0 charge, it's going to have the same number of electrons as it does protons. Okay? So, but I was with you up until that. I like that you were thinking creatively. All right. So the idea here is that as we walk along the periodic table, we're adding protons, right, with the atomic number as we go up in atom size, but we're also, for every proton we're adding, we're going to add an electron, right? So fluorine, a neutrally charged atom of fluorine, has 9 electrons as well as 9 protons. All right, so now that you've got that, let's go on to the harder question. How does the electronic structure of an atom reflect the ways that an atom can combine with other atoms to form molecules? All right, that's the question that I want to answer here. Does anybody want to take a stab at it or huddle to talk about it, or do you want me to just forge ahead? Throw it at you. I'll forge ahead here. So here is, I debated putting this up here at all. This is probably the scariest slide that I'm going to put on the screen this week. And the idea is that electrons are organized into shells. It's like an onion around the center, which is the nucleus. All right? And each of the rows in the periodic table is a different shell. Okay, so a row in the periodic table, so hydrogen and helium being that first row, that corresponds to the first shell of electrons. And there are only 2 shells in there. Imagine if we had like line dancing or something. And in the middle, we had, or like a circle dance, and you'd have 2 people holding hands, and they'd be like spinning around or dancing, whatever they're doing. And then we're going to put some people outside of them. You're going to need more people to go around. And then the next row is going to have more people. All right? This is why the periodic table looks the way it does. This is why it's not a square. All right? Each row starts adding more. All right. So I'm running out of time here.